Hello, it's day 18, and we've got a problem that I think part one we may be able to solve with a spreadsheet today. So that should be fun. So we've got a list of instructions. The color is unused as yet. I imagine that comes up in part two, but they essentially represent a going right 6 steps, going down 5 steps, going left 2 steps, and then sort of building this trench, then filling it in. Our task is to find the number of filled in squares or cells. There are a few little quirks. One is the digging. Could the digging become something? Will we have to dig down even further? I don't know. Seemingly not yet. There is also some sort of finesse in the calculation of the edges versus the interior that we need to deal with, which we'll go more into. And what was the other thing? Oh yeah, it says, when viewed from above, the above example dig plan would result in the following loop of trench. Now, we hopefully can assume that the trench will be a loop, but I'm not 100% certain that it will be. And in this situation, I think I would like to interrogate the input a little bit more to check whether it really will be a loop, in which case we get to use a simpler calculation. Or are there any intersections, any sort of weirdness? Is there any sort of weirdness going on there? So that will be important for us to interrogate before assuming that we understand what's going on. I have a bit of a process planned out. Here are the instructions from the trial. Here's the visualization. Now, based on these instructions, there are a few interesting things about them. The first is this is actually not totally dissimilar to SVG. So we can transform this into an SVG path quite straightforwardly, just using multiple cursors. So I'm going to do that, and that's how I'm going to visualize and find out if there's any loops in this thing or not, or rather if it does represent a loop or not. Second, if we find the points on the outside of this trench, which we can do, I believe, then we can use something that came up in the earlier challenges, the shoelace formula, which allows us to find the area bounded by any, what is it, of a simple polygon. So what is a simple polygon? Does not intersect itself and has no holes. So we've got to work out if it does not intersect itself and whether it has any holes or not. Yeah, so the way of applying it is essentially, I don't really know what all this means, but what I have worked out is you take pairs of coordinates, you multiply out the diagonals, subtract the this diagonal from this diagonal, add them together, and you get, and then if you divide it by 2, you get the area inside the polygon. Now, there is an additional quirk, which is if we just do the coordinates of the cells, we don't get the right answer because, and I may or may not understand this correctly, we need actually to work out the outside coordinates, and because well, I don't actually know why, but we do. So we need to work out the outside coordinates for it to be a polygon, and that is not as simple as just taking the cell coordinates, because if we go around the outside, sometimes we need to go a bit further to cover the corners, and sometimes we don't to cover the inward corners. Now, for this, what this means is assuming that I believe we're assuming that our loop sort of goes like this rather than like this, then we need to count the clockwise turns. That's the turns where it goes from left to down, down to right, right to up, or no, right. Let's look at it here. Right to down, down to left, down to left, left to up, and then up to right, for example, although we don't have that actually in this one. We need to count those turns, and then if we add up the result of the shoelace formula based on the simple coordinates. Wait, is this right? Yeah. If we take the inwards coordinates here, the cell coordinates, use the shoelace formula on that, and then add in one cell for every clockwise turn, I think less the final one, I'm not certain, then we get the right answer, I believe. Hopefully not by coincidence. In any case, it'll be fun finding out, and I think we can do it with a spreadsheet as a result. So we'll try it with that, and then I'll give myself a pause if I don't get the right answer and just calculate it out properly. There's probably other ways using flood fill and all sorts of stuff. In any case, so the first thing I'm going to do is visualize it with SVG. I'm not going to set a timer because it'll be, in fact, I'll set a timer when I start working on the spreadsheet for the input. I've already played around with the spreadsheet a little bit, of course. There is, of course, a little bit of code in there, but I'm not going to count that. Anyway, spreadsheet days work kind of differently anyway. Visualization. Let's go with this. Take the input. I'm going to switch to looking at my editor so that we can do this bit. Take this down, and then rights. Rights are they translate to a this is so SVG parse. Essentially, you can do them with relative changes, like a kind of turtle moving around, and this D field in the path tag represents a set of commands, and these commands can be move right x number. Now for right, we're taking it as a lowercase horizontal. So uppercase horizontal is an absolute move, lowercase horizontal is a relative move. Horizontal to the right, that's positive. Left, it's a horizontal negative. Up, that's a vertical negative. And down, that's a vertical positive. And then I believe this should visualize our path. So we may need to expand the view a little bit. It's actually an 18, isn't it? There we go. All right, so we may need to expand, just tweak this a little bit. Oh, sorry, I need you to see it, don't I? Let's take a look at this. All right, so this is what we've got. This is our path. There are no intersections and no loops. Good. Let's zoom this in a little bit. So I think the first point, let me I'm just adding a little square so we can see where the starting point is. Ooh. There we go. Okay, so there's the starting point by that blue square there. So we start off going right and then up, right, up, left, and then we go all the way around here. Okay. Great. So this looks like our approach will work. If we count the right hands, we're going to be, let me just double check this on our graph. Let's say we went up here instead. I think everything still works. Oh, well, I mean, we will find out ultimately. Okay, so now we can shift over to our spreadsheet. One moment. So let's actually try out with the trial first. I've not properly calculated this out. So if we take so the real input is 62. The real result is 62. All right, now let's take these all the way down. Do we actually want this? Don't actually know. Okay, weird result. That looks suspiciously engineered, doesn't it? We're always going one right further on by one. That's sort of weird, isn't it? Let me take another look at this. So what does this actually come out to? Forty-two plus 62 is 20. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15. We have 15 corners. of which 9 we know are clockwise, therefore 6 anti-clockwise. The total of this is 38. So this is all the cells that get dug -1 for the first cell. Just muddling around now, aren't they? Right. Clockwise turns. We've got 1 here, 2, 3, 4, 5, 6, 7, 8, 9, 10. No, 9. Yeah. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 clockwise turns. See, I don't understand why it might come out to that. So you could say, like the number of clockwise turns, let's say, so it's 9. 9 plus 1 times 2. It kind of gets us the right answer, but it doesn't feel very convincing. I'm mulling over whether to just try it anyway, see whether it works. Let's try it with a different trial. Let's say we do let's say we take 2 out like that. So this should decrease it by 2. 1 second. Okay, I got distracted. I'm back. I don't know what this means for the categorization of this challenge. However, um, I know it's about clockwise and anti-clockwise turns. And what I believe is that if you make a clockwise turn, you have to add 1. And if you make an anti-clockwise turn, you have to take 1 away or something like that. In any case, the logic is if the next turn is a clockwise turn, so let's say we're at this point here, or rather this point, if the next turn is a clockwise turn, you have to add 1 to the length you're going. That makes sense. If your current turn is an anti-clockwise turn, let's say we're here, you have to subtract 1. Or something. In any case, I've got a spreadsheet. Let us try it with the input. We don't need this. And where am I? Where's my input? Here we go. We can take all these out. And not go really far. Oh, and I guess we need to do this as well. Okay, and then we end up with back at 0, 1, that's good. And we end up with minus 73. Minus 73. Well, that's definitely not right, is it? It's nowhere near right. Something's very wrong. Y minus 2, yeah. Yeah, I think I may have got the formula wrong. Oh, there we go. Let's hope that's right. Ah, that is shocking. Truly shocking. All right. Now, the next one I imagine will need some programming. Much too small. Swap the color and instruction parameters when producing the dig plan. They don't have time to fix the bug. One of them asks if you can extract the correct instructions from the hexadecimal codes. Each hexadecimal code is 6 hexadecimal digits long. First 5 encode the distance of meters as a 5-digit hexadecimal number. The last hexadecimal digit encodes the direction to dig. First 5. Okay, fine. Right, so we've got to convert this to decimal. All right, well, that doesn't seem so hard. Okay, let's get straight to it then. All right. Can we do this? No. And we've got 0, 1, 2, 3, 4, 5, 6, 7. What is it? Ugh, need my spreadsheet knowledge back. Is it mid? Yes. No. Okay. For this, I'm getting 1. I actually need to start at 8, I think. That's right. No, that's not right. Okay, and then can you index into things here? Yeah, we can do this, right? So this is going to be, what is it? RDLU. Or in fact, RD ends with ULU. Great, okay. And then we've got hexadecimal on the other characters. Do we have anything like that in Google Sheets? Yes. What a joy. This is going to be from something like 2 through 7. There's actually going to be 6. We'll be starting at 3 and then going on to 6. Nope. 5. And then it's hex to deck to get this, which is okay. 937, 461, 937, 461, 937. Okay, perfect. Now all that remains is to use this in these cells. So this should now be E. They should, oh no, they don't necessarily need to be the same. These are the same. This, now these should be coming out to, instead of this, it should be the E. And instead of the column, maybe C, it should be F. And then here, it's the same transformation. F, F. Okay, and calculated output is something ending in 115. Oh, it looks good. It looks good. Okay, good. Great. Now let's dupe this. Go to the input, put our real input in. And then we take all these formula down. Take this up. And we get this number, which in theory is our winning number. Okay, all right, a spreadsheet day. Love a spreadsheet day. All right, see you tomorrow.